In section 7.6, example 1, what we've got is one charge is released from rest from another charge. So let's imagine this fixed charge here. We're going to call this Q2. It is 5.3 times 10 to the negative 8. It's positive, right? No negative sign there, so it's a big positive charge. This is Q2. I've got another charge here, and I'm going to make it small. It actually doesn't matter the sizes of these charges, but in my mind, I kind of like to imagine there's a big charge here. It's fixed in place. If it's fixed, it means it can't move. So here's my big charge. It's fixed in place. My other charge, this is Q1, and this is also no negative sign, so 4 times 10 to the minus 9. It's also positive. These are coulombs. It is 0.25 meters away, going that way, and it's going to get shoved away this way. So it's going to experience a force going this way, and it's going to end up at some location over here. And this location, let's call this one R1, it's going to end up at a location 0.35 meters. Okay, that's all the way from the start over here. So we started off 0.25 meters. We're going to end up at this location over here, 0.35 meters. It's released from rest. Okay, so V1, 0, not question mark. This V over here, let's call it V primed actually. V primed, it's this one that I'm looking for. So let's just say V and V primed. Actually, let's leave it as V. V1 and V1 primed. I'll call this guy V2. It's just 0 throughout. So V2 is 0, V2 primed is 0. Hopefully you can read those. We're not really too concerned with this. We're concerned with this guy as it gets pushed away. The question is, how fast is it moving over here? A couple things with this. We might be tempted to use forces. I find whenever we see something like this, we've done a lot of forces and a lot of kinematics. And just something to note is the force acting on this charge particle, if I put Fe right here, that force, Fe, is K Q1 Q2 over R squared. No problem, I can calculate that. The problem is, though, as this guy moves away, R changes. Okay, if this R is not constant, then when I go to use something like F equals ma, this guy here is also not constant, which means this is not constant. Okay, so these guys are not constant. That's a problem. So if this guy's not constant, that's not constant, that's not constant. Remember, my temptation is I'd like to use forces, F equals ma, so that I can use my kinematics equations. And just keep in mind, that's not constant, acceleration is not constant. These kinematics equations are the constant acceleration kinematics equations. If A is not constant because of all this argument, then I cannot use those. So I've got to find something else. In the PowerPoint it mentions, yay, we've got conservation of energy. We are going to use conservation of energy, and I'm going to have to squeeze this in a little bit, but what we've got is, let me write out the most general kind of version here. We've got kinetic energy of this guy. Now this guy also could have some kinetic energy. It doesn't, but let me just write it there just because in some examples that you do, they possibly both could be moving. It could also have some electric potential energy. There is going to be some electric potential energy between those two. And then that's kind of equal to all the kinetics and electric potential afterwards. So at position 1 versus position 2. In this case, this guy was not moving ever. So he's fixed in place. This guy started off from rest. Okay, so we're getting down to a much simpler equation. We're just going to have K Q1 Q2 over R initial. Here, this is what I'm looking for, half mv1 prime squared. But there still is some potential energy here at the end when it's over here. So we're going to have to fill those in. Looks like I'm going to be short on room here. I didn't give myself much room, but let's see if I can fit it in. So filling in numbers for this guy. We know one of the Q's is this number. One of the Q's is this number. And the distance between them is this value, 0.25. Mass of the charged particle, 9 times 10 to the minus 19. Don't forget to square. Oh, sorry, that's not, oh boy. That's not squared. This is squared. That's what we're looking for. But don't forget to square that guy. Subbing in for this guy, 9 times 10 to the 9. Our Q's are all the same, so 4 times 10 to the minus 9. 5.3, 10 to the minus 8. Our second R value, yeah, 0.35. Okay, so we're going to work out a bunch of math in here. I'm very low on room, so I'm just going to give you the final answer. V1 primed at the end, 2.2 times 10 to the 6 meters per second. That's how fast it's going. Give you a double box for this one. Again, the reason I can't use this stuff is because force is not constant as it moves, because that R value is not constant. So I can't use forces and kinematics. I also can't use work. So sometimes people say, oh, maybe I could use work. Work is like FD cos theta. Again, same reasoning, right? If R is not constant, force is not constant, this guy is also not constant, which means I can't use that equation either. So I can't use work. I have to use conservation of energy. Now I know work is related to energy. It's not that I can't use work, it's that I don't have the math for it. I can't, I need some calculus. But this version here, we have enough math, we can solve that. If I move on then to this, the next slide, I wanted to just mention this before we go on to example 2. I'll do that in a separate video. But it just kind of mentions on the slide that in a uniform electric field, which is like parallel plates, if I have a set of parallel plates, the electric field between those parallel plates is constant and uniform everywhere. I guess that's the same word, is it? Same meaning. There's an E field going from positive towards negative. It is nice and uniform all the way across, so straight lines, all uniformly spaced. I just want to draw in here, so I'm not going to continue it, but in there it's nice and uniform. Something that we'll often do with parallel plates, or scientists or whatever engineers will often do, they'll put a charged particle right next to the positive parallel plate if it's a positively charged particle, because this guy is going to repel this charged particle. Okay, it's going to experience a force going out this way, Fe, that's equal to Q times E. Hopefully you can read this, Q times E. Zoom in if you're having trouble seeing my writing. And in this case, this thing is constant, right? This E value in here is constant, which means the force is constant. So if I kind of slide back over here, I don't have this equation, but if I have this equation, then force is constant, which means acceleration is constant, which means, yay, I can use kinematics, I can use work. Okay, so this example, the difference is I've got like individual particles, whereas here I've got a set of parallel plates with a single charge particle, but that's the difference. Just something to show you, and then we'll do an example later with this. Work is then like FD cos theta. I'm going to assume that the displacement and the force are in the same direction, so this cos theta just becomes cosine of 0 becomes 1. Okay, so I'm just going to focus on this stuff. We know that this electric force is QE, and we have that D still there. We also know for parallel plates that E is delta V over R. So I'm just going to keep my fraction going out here a little bit, and I've got a D there. So just note E is delta V over R. That's what I'm using to go from here to here. And I'm going to pause right there for a sec. We'll keep going in one sec, but just for terminology, R is plate separation. D is how far did the charged particle move. Okay, so when we're talking about FD cos theta, that D is how far did the object, whatever it is, in this case the charged particle, how far did the charged particle move? That's D. This R, when we're using this equation, is plate separation. So oftentimes when we do this, like an experiment like this, I'm going to let this positive charge go. It's going to go all the way across and collide with the negative plate. Or sometimes what people will do, This is another common one. They'll actually drill a hole. Remember, this is like, again, like a big sheet of paper. If you can picture like my hands kind of being like this, kind of drilling like a hole through the center of this piece of paper. We're going to drill a hole, and I didn't line mine up, but it's supposed to be so that it can shoot right through. This is like a little particle accelerator, so I let this charged particle go. It's going to go zooming right out. So oftentimes D and R are going to be the same because it goes all the way across. So if they're not the same, if it only goes part way across, then I can use this equation. If, however, D is equal to R, then D and R can cancel. I could also just say work is Q delta V. So that's kind of another version if this is true, if D is equal to R.